Right, moving on to question 2, which is all about refraction. Okay, so what is meant by the term refraction? And again, it doesn't tell you to draw a diagram, but I find drawing out a diagram really helpful here, right? Because it reminds me of, what I need to put in my answer, right? So if I've got this situation, I've got something like that, right? So as we go from a low optical density medium, right, like air, to a high optical density medium, then lick her toes, it gets bent towards the normal, right? The ray gets bent towards the normal, right? So what's the key things that we need in our answer? The bending happens as we go from one medium to another. It's not as it goes through the medium, it's as it changes medium from one medium to another. So that's got to be part of our answer, okay? And also this idea of bending as well, okay? So something like bending, the bending of a ray as it passes from one medium to another. Okay, and of course the other thing that happens as well is that it will change speed at the boundary as well. Okay, so that's acceptable too. Draw the path of the ray of light in water. Okay, it tells you the angle of refraction is 33. Okay, and we know that we measured the angle between the normal and the ray. So that's got to be 33 degrees there. You had a protractor with you, so now would have been a good time to use it, okay, to check that, right? And of course you need to put an arrow on your ray as well. Formula linking refractive index, angle of incidence, sine I and sine R. If you weren't sure, you could have looked that up in the formula booklet that you had available. Show that the refractive index of water is about 1.3. Okay, so if we go back and we look at the question, it tells us the angle of incidence, okay, tells us the angle of incidence, which is 45. It tells us the angle of refraction, which is 33. Okay, so now we've got to push the right buttons on our calculator, okay, and it comes out as an answer of 1.298, blah, 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 like that, right? Okay, and what we've done there is we've shown that this is approximately equal to 1.3, okay? So if you did this step and then just wrote 1.3, that's not enough. You've got to show, that you've actually done the calculation, and then you're allowed to do this squiggly arrow, which means approximately the same as, and then you can write 1.3, right? Okay. And in this one, it does suggest that you draw a diagram to help you with your answer, right? Okay, so if they're asking us to do it, let's do it. Okay, I'm going to draw a semicircular glass block. Doesn't have to be a semicircular glass block, it could be anything. Okay, any sort of prism. But the idea here is that if we shining in at an angle of incidence, which is equal to the critical angle, then what will happen is the ray, the angle of refraction will be 90 degrees. Okay, so the ray will continue like this. Okay, and that's because when the angle of incidence is equal to the critical angle, that's like a boundary condition, right? Let me just change the color of my pen for a moment. If I is less than C, okay, then you'll get some reflection, but mostly refraction. But then the critical idea that we need to get across, see what I did there, critical idea, yeah, critical idea that we need to get across is that as soon as we go larger than the critical angle, as soon as we've got an angle of incidence that's larger than the critical angle, so my green is for the angle of incidence larger than the critical angle, okay, then what we're going to get is total internal reflection. Okay, so that means that T is total internal reflection. Okay, so how could we say that as a sentence? Okay, it's the angle of incidence in the slower medium. Okay, you can see that this is glass here. Okay, so that's my lower optical density medium. Okay, it's the And if you go above that angle, then you're going to get total internal reflection, right? Okay, or you could describe it in words. It's the angle of incidence in the higher optical density medium, which gives an angle of refraction of exactly 90 degrees. Okay. Again, picture's worth 1,000 words. I would definitely have drawn a picture there. And if you'd have drawn that picture, that would have got you both marks. Okay, calculate the critical angle of water. So we need to know the formula sine C is 1 over n. If you couldn't remember that formula, you could just look it up. Okay, so that gets us 1 divided by 1.33, like that. And then the step that you've got to take is you've got to do sine to the minus 1, okay, of 1 divided by 1.33. Okay, and if you did that on a calculator, it should have got you 50.3. Okay, but because there's two significant figures for the input data, we're going to give our output to two significant figures, so that would have been 50 degrees. That's the best answer there. Okay, a ray of light leaves the torch as shown in the diagram below. Complete the path of light. Now the key thing, look, they're trying to lead you into this. Like if you look at how the question develops, C part 1 is talking about critical angle, right? And it getting you to think about what happens, you know, before and after the critical angle. C part 2, they've actually got you to calculate the critical angle, and it's 50. And now in C part 3, we've now got an angle that's bigger than the critical angle, right? So we know what happens because we're bigger than the critical angle. Okay, then we're just going to get total internal reflection. Okay, so there we go. Label it up with an arrow. All right. Sorry, that bit of ray shouldn't be there, should it? Because it will refract as it comes out of the glass, right? So you just need the bit that's in water. Okay, and that's it for question 2. How do I turn it off again?